Today we are going to discuss about the solution of an important problem of group theory. And the problem is every commutative group, it is known as abelian group of order 6 must be cyclic. Okay, so we have to prove that any abelian group of order 6, must be a cyclic group. Okay, we first let a group, this is G, and let the order of G, this is equal to 6. We have to show that G is a cyclic group. That is, we have to show that there exists an element A of G such that order of G, this is equal to order of A. Okay, then G must be cyclic because G contains a element of order 6, and in this case we say that G is generated by the element A, right? And we prove this problem in so many ways, but today here we prove this problem by using very basic concept of group theory. Okay, we use here three concepts. The first concept is every group of even order have at least one element of order 2. This is the first concept. Okay, and the second concept is if in a commutative group there are two elements AB such that the order of A and order of B are prime to each other, that is GCD of order of A and order of B, this is equal to 1. Then there exists an element AB, must exist an element AB with order of AB, this is equal to order of A into order of B. This is the second result we use here. And the third result is very famous theorem of group theory, this is Lagrange theorem. And this theorem states that if H be any subgroup of a finite group G, then order of H must divide order of G. Or it is also said that order of every element A belongs to G such that order of A divide order of G. Okay. Now here order of G, this is equal to 6. So for all X belongs to G, imply order of X, this is equal to 1 or 2 or 3 or 6, because these are the divisor of 6. We use this property, right? And using the first property, there must exist an element of order 2 because 6 is an even number. Okay, since order of G is even, so there exists at least one Y belongs to G such that order of Y, this is equal to 2. Also we know that in a group there must exist an identity element. Okay, so one element E belongs to G such that order of E, this is equal to 1. Okay, now if we take, there exists an element Z belongs to G such that order of Z, this is equal to 3 or 6. Okay, if we take order of Z equal to 6, so in this case we let that there is an element A of order of G such that order of G, this is equal to order of A. Okay, so we let here order of Z not equal to 6. Okay, now if we take order of Z, this is equal to 3, then also by the second condition we say that there exists an element YZ belongs to Z such that order of YZ, this is equal to 2 into 3, this is equal to 6. So in this case also we prove this is cyclic. So we let also order of z not equal to 3. So we let first order of z not equal to 6 and order of z not equal to 3. And there exists an element of order 1 and there exists an element of order 2. So in this case all the non-identity element of G must have order 2. Okay, because it has not order 3, not order 6 and one element of order 1 and all the other non-identity element of order must be 2. Okay, and left one such element other than Y which must belongs to G and order of this element is also 2. Okay, let it be P. P belongs to G such that order of P this is equal to 2. Okay, now by closure property of group there exists X into P belongs to G. Okay, and X into P whole square this is equal to X square P square, because this is commutative group and we know that X square means E and P square means also E, because sorry, this is not X, this is Y, also this is Y. Okay, because we let here Y an element of order 2 and P an element of order 2, and so we write Y square this is equal to E and P square this is equal to E, so we get E. So we get there exists YP belongs to G such that order of YP this is equal to 2 also. Okay, and also we form a subgroup. What is the subgroup? Let H which is given by E, Y, P and YP, because closure property hold here and also all the property holds by this subgroup. Okay, and since H be the subgroup of G and clearly order of H this is equal to 4, and but this does not divide 6, so this contradicts our Lagrange theorem. Okay, so there must exist at least one element of G which have the order other than 2, because if we take all the non-identity element of order 2 then we get or we arrive at the position of contradiction. Okay, so there must exist an element of order either 3 or order either 6. If we get an element of order 6 then obviously it is cyclic. If we also take an element of order 3 then we also prove here by the second property it is cyclic. Okay, so we prove that any commutative group or abelian group of order 6 must be cyclic group. Okay, very interesting theorem of group theory. Thank you for watching.